Hello again, everybody. So it is time to continue our Chemistry Quarter 1 review. This time we will be covering Unit 2. Uh-oh. Hold up. There we go. Okay, sorry for that. So please review these study tips as well. These are very useful and great strategies to help you prepare for your test. Okay, so last time we covered Unit 1, which went from states of matter through pure substances and mixtures. So now we are going to focus on Unit 2. Let's go ahead and click that link and get started. All right, so atomic theory and the periodic table. So whenever we started Unit 2, we started by covering the different scientists and theorists that contributed to the atomic theory. And so here's a little mnemonic to help you remember them in order. Don't taste really burnt quesadillas. Okay, say that one more time. Don't taste really burnt quesadillas. Each of the first letters of the saying coincides with one of the models that we're going to need to know. So D stands for Dalton, T for Thomson, R for Rutherford, B for Bohr, and Q for quantum. Also here we have a very good picture that demonstrates each of these different scientists and their models. So we have John Dalton with his solid sphere model. He just thought the atom was a solid sphere. Then we go to J.J. Thomson, who had the plum pudding model, or as I like to call it, the chocolate chip cookie model. He believed that there was a positively charged cloud of sorts with small negative charges sprinkled throughout. Then when we go to Rutherford, we have the nuclear model, and Rutherford determined that there was a positive center to the atom and negative charges surrounding it. Then we have Bohr with the planetary model. He figured that, electrons didn't just zoom around our nucleus all willy-nilly. There are different energy levels and paths in which those electrons follow. Now, the quantum model expands upon Bohr a little further. Erwin Schrödinger conceptualized this model, and he believed that rather than following fixed energy paths, the elements had no true predictability in their pattern around the nucleus. So instead of fixed pathways, he envisioned electron clouds. So here is a little practice for your atomic theory timeline. So if we review this timeline, we see the original theorist or philosopher, should we say, is Democritus. He had the theory that all matter is made up of indivisible atomos, or atomos, whichever way you want to pronounce it. But basically, Democritus had the idea that, stuff must be made of smaller stuff. So how far does that break down? Can we break down material forever, or is there a point where we can't break it down any further? At what point do we build upon this? So that was Democritus's initial thought. And so Dalton was actually the first scientist to truly contribute to this and develop an actual model. The solid sphere model, otherwise known as the billiard ball model, and he believed that all atoms are indivisible. He defined that material that was indivisible as the atom. Then we got J.J. Thomson coming in. He discovered the electron using the cathode ray experiment. And his model, the plum pudding model, otherwise known as the chocolate chip cookie model, if you're more like me and have never had plum pudding, basically states that electrons are kind of sprinkled throughout the positive force of the atom. So negative charges sprinkled throughout. There's the bell. All right, let's continue on, though. We've got Ernest Rutherford. He conceptualized the nuclear atomic model using the gold foil experiment. He was the one that actually discovered that the nucleus of our atom had that positive charge and knew that there were protons and neutrons within the center. Then we've got Niels Bohr. He discovered the planetary model, and it's called planetary because he predicted that electrons had fixed energies and paths in which they orbited the nucleus. And finally, at the end, we have Erwin Schrödinger, who came up with the quantum mechanical model with the electron clouds. And this is the model that we currently have accepted today. All right, a little history of the periodic table, Mendeleev versus Moseley. So Mendeleev actually arranged the periodic table initially by increasing atomic weight. He put the elements in columns by the way they reacted, and left blank spaces for what he said were undiscovered elements. And he was correct. He was able to predict elements that hadn't even existed yet, strictly by the arrangement of their weight and different properties that they shared. Then we've got Moseley, who developed a new understanding of the periodic law and sort of revised Mendeleev's organization. He arranged the elements in order of increasing atomic number. Now, that is how we have the periodic table organized today. However, Mendeleev is the scientist that is mostly credited with the periodic table because he was able to predict elements and their location on the periodic table that didn't even exist yet. And he was right too. So he is our go-to guy when referencing the periodic table. So within the periodic table itself, it can be broken down into different families and categories. So firstly, we need to discuss the arrangement of metals, nonmetals, and metalloids. So metals make up about 80% of the periodic table. They are typically on the left side, apart for hydrogen. Hydrogen is a gas, so it is not a metal. Almost all are solid at room temperature. These metals are lustrous, which means shiny, malleable, able to be hammered into a sheet. So think malleable like a mallet. A mallet is a hammer. You can hammer these metals into sheets. They are ductile, meaning that they can be drawn into a wire, and then they are conductors as well. They can conduct heat and electricity and do a really good job of passing those different currents throughout. So on the left are metals, and on the far right side are our nonmetals. They're found, like I said, on the far right side of the periodic table. Most are actually gaseous at room temperature, and they're typically dull, brittle meaning they can easily break apart and shatter. And then they're insulators, so they're not conductors, but rather they are able to hold in heat and electricity more effectively. Then, of course, in between, we've got metalloids. They're found on the stair-step line, which if you look at the periodic table, you can actually see a boldened line on which either side those metalloids rest. They have properties of both metals and nonmetals, so they can be shiny, but also brittle, and they could be semiconductors. So they could sometimes conduct heat or electricity, or just do a halfway decent job at being a conductor. So they have properties of both. Periods on a periodic table represent differing energy levels within an atom. So each period represents energy levels that are actually added onto an atom. And then groups all have same number of valence electrons and similar properties. So for now, we're going to focus more on the groups and those families. And then once we get into electron configuration in our next unit, we'll explore the periods a little more. All right, periodic families. We've got alkali metals. That's our group 1 elements. Group 1 is right here, this red column, apart from hydrogen. These metals have 1 valence electron in the outermost shell. They are soft and silvery, and they are very reactive, especially with water. And they're very good at conducting electricity too. So if you were so fortunate enough to see the videos on some of these metals reacting with water, you saw exactly how explosive and reactive they can be. They have 1 valence electron in that outermost shell, which means that they're highly imbalanced, and they are trying so desperately to get rid of that valence electron so they can find balance, so they can find that equilibrium. Then in the next group over, on here, it's this orange group. These are our alkaline earth metals. They have 2 valence electrons in the outermost shell, so 1 more than alkali metals. They are white and malleable, and they're reactive, but they're not as reactive as your alkali metals, and they conduct electricity as well. Then in between, we've got this giant gray group. It is like you're transitioning from the left over to the right side, which is why they're called our transition metals. They're groups 3 through about 12. They're good conductors of heat and electricity, and their valence electrons vary because there are so many different groups. Some are used for jewelry, actually. So you're going to find a lot of your like iron, gold, nickel, copper, all of those, zinc, all of these metals are within this category. Transition metals are put up to 32 electrons in their second to last shell and can bond with many elements. So they can bond with a huge variety of elements and create all kinds of cool compounds. So really quick, we're going to do a little check to look at your understanding. All right, where are the alkali metals found? Well, we know alkali are our group 1 metals, so they are the furthest group on the periodic table on the left side. Alkaline earth metals then would be right next door, group 2. All right, the other 2 main periodic families that you need to understand are halogens and noble gases. Your halogens are in group 17. They have 7 electrons in the outermost shell. They're all nonmetals, very reactive when bonded with group 1. So they have 7. They're looking to get 8, so they will bond oftentimes with the elements in group 1 who have that 1 extra electron that they're trying to get rid of. So if you take that 1 electron, add it to the 7, you would have 8 electrons in that outermost shell, and then the compound itself would be balanced and stable. Much like our noble gases in group 18. So the group on the furthest right hand over here, this lighter purple color, those are our noble gases. They exist as gases and they are nonmetals. There are 8 electrons in the outermost shell, so they have that full valence shell. Helium only has 2 electrons in the outermost shell, but it's still full. They're not reactive with other elements because they do not want to lose or gain electrons. They're already stable as is. All right, moving forward, we're going to discuss periodic trends. So these are trends and patterns that we see of these 3 categories on the periodic table itself. So atomic radius, that's the distance between the center of nucleus and the outermost electron, or the furthest energy level. Electronegativity is the ability of an atom to gain electrons, and ionization energy is the ability of an atom to lose electrons. So this is an excellent diagram that shows you exactly how these patterns behave, because for your exam and for regular chemistry in general, you'll just need to understand how these trends interact with each other. You need the definition as well as how their relationship is to one another. So just know that your atom, your atomic size increases as you go left and down. So your largest atom is your francium down here in the bottom left corner. That's as large as your atom gets. So your largest atom is in this bottom right corner. However, the other 2 trends, your electronegativity and ionization energy, actually increase as they move up and to the right. Now, why is this? Well, the larger an atom is, the less energy required to remove or add electrons to it. If it's a huge atom, that nucleus isn't going to have a massive pull on its electrons, right? Remember Coulomb's law? It's very important, people. That's going to explain a lot about atomic structure within the upcoming weeks. So just know that your atom behaves like a magnet, and the nucleus has that positive charge in the center, and your electrons are negatively charged on the outside. So since they are opposite charges, they attract towards each other. Now, the closer your nucleus and your electrons are, the more energy is going to be required to remove or add in additional electrons. There's already such a great pull between them, it's hard to separate or to adjust. On the other hand, if your nucleus and your furthest electron are far apart, the atom itself is huge, it's not going to require as much energy to separate those electrons or add in more electrons. It's a lot easier when they're further apart. So there's atomic radius again, distance between 2 adjacent atoms divided in half. That's a pretty over-the-top explanation for the radius of an atom. It's from your center of your nucleus to the outermost energy level. So from the center of your nucleus to your outermost electron, that's the measurement we're looking for. We already discussed the trend. It increases as you move down, increases as you move down, and increases as you move left to right. This diagram does a great job at showing that our elements in this bottom left corner are the largest. So let's go ahead and do a little practice. Okay, so we've got calcium, which is right here, atomic number of 20, and barium, which is atomic number of 56. So because barium is a little lower, you can actually look, it's got 56 protons versus 20 protons. That means that it's got a bigger atom itself, strictly because it's got more protons in the nucleus. Barium, therefore, has a larger atomic radius than calcium. All right, electronegativity, the measure of the tendency of an atom to attract electrons, the desire an atom has for electrons in a bond. So while we said that this bottom left corner has the largest atomic radius, the top right corner has the greatest electronegativity value. It decreases as you move down and increases as you move left to right. So let's go ahead and practice really quick. All right, which of these following elements has the higher electronegativity? We've got fluorine or boron. Well, since fluorine is further right, it's further on this top right side, fluorine has more electronegativity. And then finally, we've got ionization energy. This is the amount of energy required to remove an electron from an atom. It's like you're pulling the magnet apart. You're trying to remove an electron. So ionization energy is going to be very similar to electronegativity. Even though they do the opposite thing, it depends on that size of the atom. So ionization energy, again, is the greatest in this top right-hand corner. It increases as you move left to right and bottom up. So one more practice. All right, lower ionization energy. You have to be very careful how you read this. Lower ionization energy. We've got chlorine and argon. So you might think, oh, well, it's chlorine because it's further left. Well, keep in mind, argon is very balanced. It's a noble gas, so it's not trying to adjust its electrons in any way. Therefore, argon will actually have the lower ionization energy. All right. Getting close to the end here, people. Stay with me. Now we're going to cover some isotopes. Woohoo! So keep in mind, isotopes are elements with different atomic masses due to their differing number of neutrons. So if we look over at this elemental square really quick, we've got our symbol and our name. We know this is carbon. The atomic number, your atomic number is your number of protons and your number of electrons. A equals P equals E. So this atomic number defines how many protons and electrons we have. The electrons can change every now and then, but for the most part, it'll be the same value. However, this value, your atomic number, will always represent your number of protons within an atom of this element. So carbon will always have 6 protons. If I look at the periodic table and I pick any number, if I say, 17, 17 is chlorine. So every time we see an atom that has 17 protons in the nucleus, we know that it is chlorine. Now, that's how you discover and determine your protons and electrons. And so, on the other hand, if you have your mass and your number of protons or your atomic number, you can also find your number of neutrons. Our mass number is our neutrons and our protons added together. And so if we take our mass and subtract that number of protons, we can discover our number of neutrons. So 12 minus 6 would give us 6 neutrons. So let's do a little practice real quick. All right, here's a great example of practicing average atomic mass. So keep in mind, even though you might have several different isotopes of an element, just because you have many different values does not mean that they all are equal in their percentage. If I had two isotopes, that doesn't mean that they both exist like a 50-50 split. Right here for isotope sulfur, different sulfur isotopes, they exist at different percent abundances, meaning that like sulfur 32 is 95%. So most of the time when you are looking at a sulfur atom, most of the time it will be an isotope sulfur 32. So let's go ahead and check out this calculation real quick. So when it comes to calculating the average atomic mass of several isotopes, there are 3 steps. Firstly, you multiply each isotope's mass times the percent. So mass times percent, mass times percent, mass times percent. So that's step 1, multiplying each isotope's mass by the percentage abundance. Step 2, you add up all those individual values then. Once you've multiplied your different isotopes, you add the totals together. Then step 3, you're just going to take that large sum and divide by 100. Since we're working with percentages, we got to make sure we divide by 100 at the end. And then your average atomic mass should be the correct answer. If you want to check, you can always look on the periodic table for that element and see how close you are. All right. Finally, we've got quantum. This is our last unit. Woo! So, quantum, there are just a few key points you need to understand for the exam. Firstly, you need to understand the relationship between wavelength and frequency. They have an inverse relationship. So the example I like to use in my class is if you have a pen or a pencil, right? Like if you have a wooden pencil and you are waving it around, right? You're waving it around. If you are slow with it, the waves will be large, so your wavelength increases, but your frequency will decrease. The waves are so big, you can't have as many of them. Versus if you decrease that wavelength, if you make your waves a little smaller as you're wiggling your pencil, the size of the wave goes down. However, the frequency actually increases. So they have an inverse relationship, meaning that as one increases, the other decreases. All right, so you're going to give yourself a chance to practice really quick. Go ahead and drag your icon to the side of the spectrum that has a short wavelength. All right, drag your icon that has a long wavelength. What part of the spectrum has a long wavelength? And then which location has high energy? Okay, this is important to discuss. So know that energy and frequency have a direct relationship, a directly proportional relationship. So if you have high frequency, that means you have high energy. Think about waving the pencil around again. The more energy I put into waving the pencil, the greater frequency that I will see in my waves. Then let's look at low energy and low frequency and high frequency. All right, people, you have survived. Everybody take a deep breath. Excellent. Yes, so there is only a couple links on here currently. I'm in the process of adding more, but you will have additional resources over Unit 1 and 2. These are different videos that you can watch if you need a little more information or you just want to hear a different perspective on it. But as always, your best source, your best resource are your teachers, right? They are the ones that are teaching you the material and the ones that came up with the test. So if you have any questions, they're the ones that you need to go to. Also, don't forget to reference those study tips at the beginning if you need any more pointers, but otherwise, that is all we have. Thank you so much for reviewing these videos. Have a great day and good luck. You're going to do great on that test.